Hello students, welcome to the course Network Theory. So in this video, we start off with Thevenin's theorem. The very important theorem in linear circuit analysis is Thevenin's theorem. Okay. The main objective of Thevenin's theorem is to reduce some portion of a circuit to an equivalent source and a single element. Okay. So whatever may be the complex circuit, okay, so that we will convert it into an equivalent circuit. Okay. So it will have a single voltage source in series with some element. Okay. It may be an impedance or a resistance. So this reduced equivalent circuit connected to the remaining part of the circuit will allow us to find the desired current or voltage. Okay, that means we'll have the complete closed circuit into two. That is, load we will separate, we'll make it, and then we'll find the equivalent circuit, and then we'll connect it back the load, and we'll find the required current or voltage. Okay, so that is what the objective. That's why this theorem is based on circuit equivalence. Okay, so we'll understand this when we come to the problem stage. So how to do this, all these things we'll come to know. Okay, a circuit is equivalent to another circuit exhibits identical characteristics at identical terminals. So always circuit equivalent means what? So we are just going to change its new value, but it is not going to affect the final output. Okay, even the original circuit, when you do the calculation current or voltage, and after the equivalent circuit, whatever you find, it will have the identical things. Okay, that's what we call it as equivalent circuit. Okay, so this theorem is due to a French engineer called as M.L. Thevenin. Okay, because of his name, so this name has come. So he was working in telegraphy and published the statement of the theorem in 1883. Okay, so this theorem greatly simplifies the analysis of linear circuits. Okay, so we'll try to understand what is the statement of M.L. Thevenin. Okay, or Thevenin's theorem statement. Okay, so it is a detailed statement. Okay, looks like very lengthy, but it is elaborated in neat manner. Okay, simple manner, lucid manner, it is explained. Okay, so from here to here you have to write the statement. So what is statement? Any linear bilateral network, however complicated it may be, connected to a load impedance, may be replaced by a simple equivalent circuit. Okay, and that simple equivalent circuit is containing a voltage source and an impedance in series with it. Okay, so previously we told objective is to make circuit equivalence, right? So what is that equivalent circuit? We are defining clearly here. It is an voltage source in series with resistance. That means a practical voltage source. So how to find out these new voltage value and current impedance value? That is the second part statement. Okay, the voltage of the voltage source is equal to the open circuit voltage. Open circuit voltage means load is removed, and then we have measured the voltage, that is called as open circuit voltage across the load terminals, and the value of the impedance. Okay, so this series we have told impedance. No, two parts are there here. First, you need to calculate voltage, new voltage value, and then new impedance value. So the voltage value is nothing but open circuit voltage across the load terminals, and the impedance is equal to the equivalent impedance of the network as viewed from the load terminals into the network, replacing all the voltage sources by short circuits and internal impedances and current sources by open circuit. So this completely meaning deactivating the sources. If it is a voltage source or current source, we will deactivate it. So when you deactivate it, what you will have? So you'll have a completely a resistive element, or it may be RLC element, no sources, right? So then you can easily, using series, parallel, or star delta transformation, anything, you can find out the this one. Okay, equivalent impedance you can find out. So then you can connect it back. Okay, so then how it looks like, the new voltage source in series with impedance and the load. Okay, so then easily you can find out the required desired or current or voltage. Okay, one more time I will repeat this. A linear bilateral network, however complicated it may be, connected to a load impedance, may be replaced by a simple equivalent circuit containing a voltage source and an impedance in series with it. So this is the first part. Okay, second part, what we have to do, how we are going to find this value. The voltage of the voltage source is equal to the open circuit voltage across the load terminals. Okay, that is the voltage part, and the value of the impedance is equal to the equivalent impedance of the network as viewed from the load terminals into the network, replacing, okay, it is elaborated here, all the voltage sources by short circuits or internal impedances and all current sources by open circuits. Okay, so that is the deactivating meaning that we have done in superposition theorem also, right? Deactivation, voltage sources are shorted, current sources are opened, right? So but here it is a different manner. Okay, so to understand this statement, the next level we'll do the proof of this. Okay, in this statement will do the proof, and you will understand some percentage better than this statement. After that we'll solve the problem, so you'll understand more clearly what is this theorem is about. Okay, so normally the trend will be, so we should take one problem and then we can do the theorem, but it is not good, so we'll go in this manner only. Okay, so please bear with me. So once you've done the problem, you can come back and read it, so you will understand it easily. Okay, so no need to by heart also. Okay, so it is a very simple English statement, you can write it. Okay, fine. So just we'll illustrate this whatever I have explained. Okay, that's what in the first part you had a linear bilateral network, however complicated it may be, I told, right? So that is what the complex network I have connected with load impedance. So this is the circuit. Okay, so this is the terminal voltage here across this bilateral network. Okay, voltage and the current. Okay, so this is converted into a simple equivalent circuit of an voltage source in series with impedance. That's what written here. Okay, impedance, and this side load is connected. Okay, so to find the voltage here, what we do, so this load will be removed and we look at the voltage of this complicated network. So we'll like that we'll look at. Okay, so except load we'll look at from this side and we'll see the VTH. Okay, or some books they will use V, some books they will use E. Okay, anything you can use VTH or ETH for Thevenin's equivalent voltage. That's why TH is the subscript. Okay, either T will be used some books, okay, or TH will be used. Okay, so I will use the standard notation, that is TH. So this is the impedance. To find out this, so we will be deactivating all the voltage sources, current sources and voltage sources will deactivate at a time, and just we'll look at the impedance, how they are connected, series parallel combination, star delta, whatever. So final equivalent impedance we are going to find and we'll place that value here. And whatever load part was there, normally it will be a resistor or a RLC combination, right? So that will be placed over here, and then you apply the KVL here, so you'll get the required voltage or current you desire. Okay, so this is the illustration of that statement. So according to Thevenin's theorem, a complicated network connected to a load impedance ZL of figure A can be replaced by the one shown in figure B. So this is equivalent to this. The circuit to the left of the terminals AB in figure B is known as the Thevenin's equivalent circuit. Okay, so this left of this AB, okay, whatever this is called as Thevenin's equivalent circuit, that is voltage source in series with impedance. This is already there in the circuit that we have removed first to find out the VTH and ETH, and then finally we have connected it back. Okay, so this is about the Thevenin's equivalent circuit. Okay, so now to prove this, we'll take one simple resistive network and we'll try to prove, okay, so this theorem. Okay, so again this theorem is asked in exam, state and prove Thevenin's theorem. That's why I'm taking this part today. Okay, so consider a network shown in figure C. So already two figures we have seen there, so figure C I will make. Okay, so this is a voltage source. I have one voltage source E, and there are three resistors are connected, R1, R2 and R3. I am doing it in general way only. Okay, and there is a load resistor RL. So now we need to replace this E, R1, R2, R3, this complex network. So simple network only I have taken. This can be done to any complicated network maybe. Okay, so this complete network, whatever I have to convert it into an single voltage source in series with the impedance or resistance here. Okay, this is what the Thevenin's equivalent circuit. Okay, so this is VTH and this is ZTH. Okay, so load will be removed in the beginning and finally it will be connected to find out. Okay, so this is the idea. So just note down this network and follow along with me to do the derivation. Okay, so how we do the derivation is, so first we will do the calculation. Okay, so I1 and I2. So I2 will be the load current here, right? So load side it is there I2. So we'll use the mesh analysis and we'll solve it and we'll write the final expression in terms of I2 and E, R1, R2, R3, RL, all this in one single line. Then we'll take the Thevenin's equivalent circuit, what is desired. Its KVL we'll use, okay, apply the KVL and we'll write equation. Then we'll compare the equation of this and that. So that is the proof for Thevenin's theorem. Okay, clear? So just follow me, so you'll understand. So from figure A, okay, so what is the figure A? Sorry, I maybe made mistake here. So figure C it is. Okay, so this figure from figure C. So we are applying KVL here. KVL, you remember, mesh analysis. So we'll use the general equation only because it is a planar network, right? So minus to plus is there. So anyhow you can take, okay. So E, okay. So it will be E equal to, so I have written straight away here. Then what you have, current here, self, right? So what is the self current? Self resistance R1 and R3 into I1. That's why plus I1 R1 plus R3, and this R3 is between I1 and I2. That's why it will come I1 minus I2, right? That's why it will be minus I2 R3. Okay, so direct equations I have written. Hope it is understood to you. Then similarly second equation is written, so there is no voltage sources here. That's why it is 0 is came. So previously I used to write this part first, and right side I used to write this E and 0. Okay, just interchange, no other difference. Okay, so 0 equal to, now here R3 is between mesh 1 and mesh 2. That's why it is minus, mutual, right? So minus I1 R3 plus I2 into all the self resistance. There are three resistors are there, R2, R3 and RL. R2 plus R3 plus RL. Make this as equation 1 and 2. Copy down. Okay. So now next what I will do. So here 0 has come. So what I will do is this I1 I will take right side. Okay. So then it will become plus I1 R3 equal to I2 into R2 plus R3 plus RL, right? So then what I will do, so I will make it for I2. So I2 is nothing but what? I1 only I will do. Okay, what is I1 then? R2 plus R3 plus RL into I2 by R3. So this I will substitute back in this equation 1 where I2 is there. Okay, from this equation, and then I will get a complete expression. Okay, all the elements of the circuit will come in single, because this complete equation only I have substituted here, right? So that's why it will become a single equation, and that will be the final equation. We will simplify it and keep, and then we'll compare it with the Thevenin's equivalent circuit. Clear? So now next step I may not be written straight away. Okay, so you do it one step here. Okay, I1 R3 you take this side. From that I1 is equal to I2 R2 plus R3 plus RL by R3. Okay, that's what I have written from equation 2. I1 is equal to, straight away I have written R2 plus R3 plus RL by R3 into I2. Make it as equation number 3. Hope it understood. So you got from question equation number 2. Now substitute this value of I1 in equation 1 where you have I1. So again here what I have made, some changes I have made because I need to find the I2 current. No, so for that what I have done, this E was right this side and this I2 was this side, right? So that's why I have interchanged it. Okay, I1 and I2 I have interchanged it. Clear? Just to show you once again. So here this E is taken this side. Okay, oh sorry, I1 is taken this side. I1 is taken this side. E minus I1 R1 plus R3 equal to this I2 R3 as it is, minus I2 R3. That I have written left side. Okay. Okay. Minus I2 R3 E minus I1 R1 plus R3. So I2 R3 left side no changes. Here I will substitute for I1 this value from equation 3. R2 plus R3 plus RL by R3 into I2. I2 I have written here. Okay. And this R1 plus R3 already there in this. So that is written. So now do the multiplication, take the LCM and finally simplify it. That will be the next equation. So I2 R3 is equal to, now LCM taken. So E into R3 minus I2 I have taken outside here, and all the resistors I am multiplying here. So first R1 with all the resistors. So R1 into R2, R1 into R3, R1 into RL till here, right? Then R3 into each of the resistor. R3 into R2, R3 into R3 is R3 square, R3 into RL. Okay, so this is RL. Clear? So note down properly. Divided by R3. So this R3, whole R3. Okay. So now we'll cross multiply this. Minus I2 R3 into R3 is minus I2 R3 square equal to this equation will come. I have straight away written. And this complete equation I have taken left side becomes plus, minus part will become plus. So here only R3 square term I have separated out because I can cancel out with this. That's why I2 into remaining as it is I have written R1 R2 R1 R3 R1 RL R3 R2 and R3 RL written, and this I have multiplied I2 into R3 square taken outside so that I can cancel out this and this. And the right side what you have ER3. Okay, so this I have taken that side means right side what is left out E into R3. Clear? So now what I will do, I will group here. Okay, so there will be R3 in this term also. Okay, R1 R3 R through R3. So I can write it as R3 common R1 plus R2, and in this two equation RL is common, right? So you can take RL common R1 plus R3. So I can whole equation I will divide by R1 plus R3. Okay, so we will see what you will get. Okay, so remember this equation. I don't have this equation in next page, so you have in your notebook. Okay, pause the video and you can note down. Okay, so I2, so that's what I have taken the common things here. R2 R1 plus R3 plus R1 R3 plus RL R1 plus R3. Okay, so R2 I have taken. Okay, sorry, R3 I told, R2 I have taken, R1 plus R3. Like that I have taken ER3. So now throughout the equation I will divide by R1 plus R3. What will happen? So individually. So here R1 plus R3 is there. So what is the cancel out, right? So R2 will come. So here denominator nothing is there. So R1 R3 by R1 plus R3 will come. Here R1 plus R3 cancel out. So RL will remain. Okay. So here E into R3 by R1 plus R3 will come. So now what I want is the equation for I2. Okay. That is the load current, right? So I2, what you will get from this? It is right side E into R3 by R1 plus R3. And here I have R2 plus R1 R3 by R1 plus R3 plus RL. Okay, so make this as equation 4. So this is the equation of the first circuit, figure C. Okay, so now what we will do, we will find out the ETH and ZTH. Okay, so what was the circuit you had? Okay, so this was the circuit you had, and you had the load. So now to find out ETH, what I will do, I will remove the load here. Okay, so this will be made open circuit. So this will be made open circuit, and here you have the voltage, right? Plus minus E, plus minus E, that will become now ETH. Okay, so this is E now, let it be. So this is R1. So you can write this picture. I have not written this. Okay, so understanding it is R1, R2, R3. So this is called as open circuit voltage here, VOC. Okay, so this is the open circuit voltage, and it is also called as Thevenin's voltage. Okay, VTH or ETH, whatever. Okay, I have taken ETH here. You can better use that only. Okay, ETH. So now what is ETH here? If you look at the figure here, so when it is open circuited, so there is no current in this branch, right? R2 current, there is no current. So this is like a zero voltage here. So current is zero, so voltage is zero here. So there is no, so this is not like not there in the circuit itself. So now what you have circuit here is E and R2, R3. So this is a series connection now, R2, R3. Okay. So now we can use the voltage divider rule. So this E voltage is equally divided among, not equally, with a voltage divider rule, it is divided among R2 and R3. So use the voltage divider rule. So that's what done here. From figure C, the open circuit voltage at terminals AB is from voltage division rule. Okay, so we have learned it in basic concepts. What is voltage division rule? So you can recall that. Okay, formula you can recall. So ETH, that is what the looking from this side, open circuit voltage is equal to, so where we are looking at the terminals R3, right? So that's why this is the resistor now. So total voltage is E. So that's why E into R3 divided by sum of resistances. So R1 plus R3. So this is what the equation. So make this as equation number 5. Okay. Hope it is clear. Similarly, we'll find the ZTH. So impedance measured between AB terminals with all energy sources eliminated, but not their impedances. Again, you draw the circuit here. I have not done it to explain it here neatly. So you have the resistors here. Okay. So 3 resistors and voltage source was there. So voltage source will be deactivated by short circuit. So I will make it short circuited. And now from this terminal, I will look at how the resistors are connected. That will be my Thevenin's equivalent resistance, or ZTH, RTH or ZTH. Okay, so here I have used RTH, so we'll strictly follow this. So these are the values of the resistors R1, R2 and R3. So here this R2 is a open element, so this is not connected to anything, so that's why it is not in it is connected. So how it is connected? It is R2, here there is a branch, so these two resistors are in series. R1 and R3 are in parallel, R1 and R3 are in parallel, and this parallel connection is in series with R2. That becomes your RTH. Okay, so that's why it is written straight away here. One step you can write, it is RTH is equal to R2 plus R1 is in parallel with R3. Okay, so this parallel. So what is the two resistors in parallel? What is the formula? The multiplication of two resistance divided by total resistance. That's why R2 plus R1 R3 by R1 plus R3. So this is the equation number 6. So these two circuits I have not done it, so you can write it for your understanding. Okay, so here you cannot measure with current 0 and all. Okay, so resistor, how they are connected, equivalent resistance we are finding. So it is Rn and R3 are in parallel, and this parallel connection is in series with R2. Anyhow you can write. Okay, so now from equation 5 and 6, neatly observe here. From equation, substituting value of equations 5 and 6 in equation 4, previous equation, if you see, so this is the denominator part there. Okay, this is the denominator part here, R2 plus R1 R3 by R1 plus R3 of RTH. So this complete value, it becomes now RTH. Okay, so this is RTH. And what is this value? Equation 5 here, E into R3 by R1 plus R3 is nothing but what? ETH. That is nothing but your numerator. Okay, so this value is nothing but ETH. Clear? So that equation, we'll write it now, that you make it as equation number 7. That is the final equation of this circuit. Okay, so substituting value of 5 and 6 in 4, you get I2 is equal to ETH by RTH plus RL. So make this as equation 7. Okay, so hope this is clear, understood to you so far. Okay, not done, you can just rewind it and you can see the video. Okay, so we'll go to now find the Thevenin's equivalent circuit now. Okay, so what is Thevenin's equivalent circuit? If you write the Thevenin's equivalent circuit according to Thevenin's theorem, so the complete, whatever complicated it may be, it can be replaced by a simple equivalent circuit having an voltage source ETH in series with impedance. So here RTH. So whatever value I have taken there, same thing I have taken here to compare it. And then there is a load is there, RL. So now it is connected back. So now you apply the KVL here with current I2, same current we are taking. So what you will get? Applying KVL we get. So here ETH minus I2 into RTH minus I2 into RL. Okay, equal to 0. So from this I2, so you take these two right side and I2 is common, RTH plus RL will come. So from that I2, if you write, you will get ETH by RTH plus RL. Okay, so make this as equation 8. So what you observe? Previous 7 equation, that is the total circuit, and now this is Thevenin's equivalent circuit. So this is normally won't change. Okay, this Thevenin's equivalent circuit equation normally will be same. Maybe current may change. So some cases they will use IL, or some cases they will use I3, or I just they will use whatever. Okay, but these values will be same, ETH, RTH, RL. That's why this equation is common equation. Okay, even in Millman's theorem we have used it, final current finding out, right? Single voltage source in series with resistance was there, but there we have done using formula, right? There are multiple Millman's theorem applicable when there are multiple sources are connected in parallel, right? So now it is circuits are connected in different fashion, that is converted into a single voltage source in series with resistor. So for that current also we got same. So finally from equation 7 and 8, so figure D is the exact equivalent of figure C. This is proved. Okay, so hence Thevenin's theorem is proved. Equation 7 and 8 are same. That's why you can, any complicated circuit you can replace it with by a Thevenin's equivalent circuit. Okay, so this was done in 1883 only. So you imagine, so we are in 2020 now. Okay, so its applicability is still in use in all your devices, circuits, everywhere. Okay, fine. So that's why it is very important theorem I told you. So now statement and proof and understanding the part understood some percent, okay, 50% I can say, okay. So to make it now to 90% or something, okay, or 80% or 70% something, we need to do problem. But when it becomes 100%, when you are able to solve your own problem, okay, when any network is given, when you do it, no, in exam you score it, right? That is the ultimate. So you have done work, okay, you have solved some problems from books, question papers, and you got the grip, okay. So then it will be your 100%, okay. So this subject is a 100 out of 100 taking subject because it is a mathematics, okay. Nowhere you can lose the marks here as a theory, okay. Even the statement and proof theory question also they will ask, so they could not miss you any step if you miss, okay. So 100 out of 100 is possible in this subject, so that's why you can work towards that, okay. So now we'll understand the action plan for using Thevenin's theorem. That means problematic part, how, okay, some procedure is there, so that I will try to discuss and wind up. Okay, so divide the original circuit into circuit A and circuit B. Okay, in general, circuit B is the load which may be linear or non-linear. So B is load will be there. Okay, circuit A is the balance of the network or remaining of the network after removing the load. Okay, exclusive of load and must be linear. Okay. In general, circuit A may contain independent sources, dependent sources, and resistors or other linear elements. Okay, it may have inductor, capacitor also. So this is the original circuit. So it will be broken into circuit A and circuit B. Circuit B will be normally load, and except load, everything will be there in A. So now these are terminals are mentioned here: A, B, X, Y, Mn. Different names will be given. So now we will first part we will divided it. Okay. So then second step, we'll separate circuit A from circuit B. So just the circuit B part I have removed here. Okay. So now, so you got the circuit and open terminal as I have done in proof also. Okay. So now what you do, sir, replace the circuit A with its Thevenin's equivalent. What is Thevenin's equivalent? Voltage source in series with resistance. Okay. So when you got this circuit A, whatever may be the combination of resistor, voltage source, current source, anything, you will bring it in this form. This is the Thevenin's equivalent circuit. Then finally what we will do, we'll reconnect the circuit B to this Thevenin's equivalent circuit, and then we'll find the our value of interest. That is what we have done in proof. So this was their ETH RTH. For that we have connected the load here, right? Circuit B means normally it is a load or combination of any element. So now if you apply the KVL here, so you'll get the voltage you require or current you require, that you will get easily. So this is the normal step. Okay. So here one more catch here is, so finding RTH will change here in different situations. Okay. So there are three scenarios are there finding RTH. So now we told, okay, so RTH we have told in proof. Okay. But there were only independent sources were there in this example derivation. But there are cases are there, like there is no independent sources, there is no dependent sources. Such cases will come. With respect to that, I have three steps here. Procedure for finding RTH. Okay. So this I will again take up when I do the problems of each kind. Okay. So that I will do in the next. So first step, three different types of circuits may be encountered in determining the resistance RTH. First case, if the circuit contains only independent sources and resistors, that is what we have taken in proof. Okay. So what we'll do, just deactivate the sources and find RTH by circuit reduction techniques. We have seen in proof, we removed the E and there were R1 and R3 in parallel and R2 in series with that, right? Easily we find out, no issues. Okay. So in that case, independent current sources are there, we deactivated by opening them, and independent voltage sources by deactivating by shorting them. That's what we have done. So this is the technique what we have done in proof. In general, question is asked, but complex questions will come. What is that? That is the second case. Second case, we'll see if the circuit contains resistors, dependent sources also will come along with independent sources. There are dependent sources along with independent sources. Then how to deactivate dependent sources? It is not possible, right? That's why we need to follow some other steps. What is that? There are three sub steps are there. First, determine the open circuit voltage VOC with the sources activated. Okay. So that is like a Thevenin's equivalent voltage. Okay. So that we will find out. Then what we'll do, find the short circuit current ISC when a short circuit is applied to the terminals AB. So to find out RTH here, so we'll short the terminals AB and we'll write a ISC. Okay. And then we'll take the ratio VOC by ISC, that will become your RTH. This VOC is almost equivalent to ETH, whatever you have find out in first part. Okay. Only IS you need to find out here with AB terminal shorted now. Okay. And that ratio, if you take the value, you will get the RTH. This is in the case of when there are dependent sources along with independent sources. Okay. So this will example I will take, okay, to understand it. Then there are third variety. If the circuit contains resistors and only dependent sources, there is no independent source at all. In that case also you can find out the Thevenin's equivalent circuit. So there are again three sub steps. First, so there is no independent sources means open circuit voltage is zero because there is no energy source straight away. So in that case, how to find out ratio? So for that, we'll connect a 1 amp current source to terminals AB right side and we'll determine VAB. So we'll find a VAB value. Then we'll take the ratio RTH is equal to VAB by 1. Okay. So VAB by 1 because current is 1 and voltage we have find out. So VAB by 1 is equivalent to RTH. Or another method in this, instead of 1 amp current source, you can add 1 volt current voltage source also. 1 volt voltage source you connect to terminals AB and determine the current IBA. So which is the current flowing from B to A. So when you measure that, so take the ratio RTH is equal to voltage is 1 because it is Ohm's law, right? R is equal to V by I. So V is 1 volt and current you measure. If you take this ratio also, you'll get the RTH. Okay. So these are the three steps. So this is the theory part of the Thevenin's theorem. Okay. Action plan, statement and proof. And these are the three methods to find out the RTH. So in all these cases, so your Thevenin's equivalent circuit will not change. Okay. So for all the cases discussed above, the Thevenin's equivalent circuit is as shown in figure. So that is having ETH in series with RTH. Okay. So in the case of third case, okay, there is no voltage source means this will come as 0. Okay. So this will be short circuit and only a resistor will come and fit over there. Okay. That is the idea. Fine. So hope you have understood some percent. Okay. Not completely, but I suggest you to go through this and write down. Okay. And next class we will do the different problems here. Okay. So first we'll take the determining RTH, only independent sources and resistors, whatever we have done in proof, such kind of problems we'll do. Second case, we'll consider dependent source along with independent sources. And then third cases, no independent sources, only dependent source and resistors. So how to connect 1 volt and finding that part we will do. And finally, we'll see some problems of AC networks. Okay. There are some other than resistive elements also there. We can apply the Thevenin's theorem. Okay. So the next 3 to 4 videos may be regarding problems on Thevenin's theorem because this is very important theorem and understanding this, each of the step is very important. Okay. So 1 or 2 problem if you done, you can do any number of problems. Only thing is we are playing with only 5 elements here. Energy source, current source, dependent sources are LC. Okay. So that's why you should be easy to do that. Very easy subject. So your doubts, everything you keep it in your notebook. Weekly once you can come and visit me. Okay. In the college I am available above your CAD lab. Okay. So above the CAD lab, I will be sitting in room number D4, I think. Okay. Maybe D4. Okay. Diagonal is there. I will be sitting there or anybody you can ask my name and they will tell you the chamber. Okay. You come and ask. Okay. So already I have done the module 1, basic concepts I have done, module 1 I have done, and module 2 already I am doing the third theorem. That means half of the module is done now. Okay. So that's why doubts are there. Just note down any problem is there if you want to verify. Okay. So WhatsApp you can send and ask a little bit, but not completely. If you are not satisfied that, you can come and ask weekly once. Okay. Any day. Okay. So Saturday to Thursday half day and remaining all 9 to 5 except 1 to 2 lunch hour. Okay. So you can come and ask. Okay. And clarify your doubts. Okay. So it will be fruitful for you. Okay. Because although it is lockdown this semester may be, however it may be going, so don't think lightly with this subject. Okay. Because whatever you have in third and fourth semester, they are very fundamental subjects and this is required for all your public sector examinations, gate examinations. Okay. Everything. Okay. So that's why this subject is very, very important and work hard towards that. Okay. And I am also putting the hard work and daily sending one video to you with neat explanation. Okay. I hope you are satisfied with this. Okay. And we'll continue doing the work as till the college are reopened. Okay. Thank you. We'll see in the next video.